to the defense of my master's thesis titled A Heuristic to Reduce the Maximum Work in Progress or Aircraft Maintenance. I'd like to thank everyone for attending either here in person or remotely. I'll start by giving a brief outline of the presentation. I'll first introduce the project by giving some background and providing a problem statement. Then in the methodology section, I'll discuss the heuristic algorithm I developed, including some intuition behind the algorithm, the sub-algorithms that make it up, and an example. And then I'll discuss the results of the algorithm and conclude by offering suggestions for future research. All right, so we'll start with the introduction. Aircraft, just like anything else, need to be maintained. This takes time and resources. Air logistics complexes are responsible for scheduling the program depot maintenance, or PDM, for aircraft fleets. Often, aircraft require scheduled maintenance within a certain window of flight hours. And once an aircraft has reached this number of flight hours, it needs to come in for maintenance. The initiation of new modification programs, aging aircraft fleets, and demand for new work all impact depot maintenance. When maintenance is poorly scheduled, it can overwhelm an ALC and lead to unnecessary downtime for aircraft that cannot be used. Now, RAMP is a simulation tool developed by Mercer Engineering Research Center. Simulation tools like RAMP can be used to visualize the performance of PDM schedules, and by analyzing the outputs of RAMP, we can modify schedules to improve them. This thesis details an algorithmic procedure to analyze RAMP outputs and improve PDM schedules. So for a bit of background, PDM scheduling is an example of a job shop problem. It's a type of combinatoric optimization problem that involves assigning multiple jobs to multiple machines. In the context of PDM, aircraft take the role of jobs, and maintenance docks take the role of machines. GSPs allow for jobs to have a required sequence of machines. For example, in figure 1, job 1 requires machine 0, machine 2, and machine 1 in that order. Job shop problems are an example of an NP-hard problem, meaning that no known polynomial time solution exists. Because of that, many heuristic and meta-heuristic algorithms have been developed for solving them. Some example meta-heuristic algorithms include neural networks, simulated annealing, genetic algorithm, and taboo search, among others. As mentioned, RAMP is a simulation tool developed by Mercer Engineering Research Center. It is a discrete event simulation tool intended for use by ALCs. RAMP is built inside Arena, which is a simulation software. RAMP allows users to control many parameters, including the machine sequences and induction schedules. This allows for a variety of simulations to be run and compared. RAMP outputs many statistics, including the number of aircraft in the system at each time step, the aircraft queue lengths, and the average flow days for each aircraft. Figure 2 shows an example output of RAMP. The blue line tracks the work in progress, or WIP, over time, and the red line tracks the total queue. Because the developed heuristic utilizes a numerical differentiation technique and an application of a second derivative test, it's worthwhile to briefly review these ideas. Derivative tests are a calculus technique for finding local extrema of smooth continuous functions. Figure 3 demonstrates an example. Each extrema occurs at a point with 0 derivative. The minima have a positive second derivative, while the maximum has a negative second derivative. These extrema tests rely on having well-defined derivative operators. The standard deviation is only defined for some continuous functions. The standard derivative is only defined for some continuous functions and doesn't apply at all to discrete functions. Derivatives are further challenged by noisy functions because they tend to amplify noise. Numerical differentiation has been well studied to solve these issues. This problem, however, is ill-posed, and there is no unique, well-behaved solution. Thus, there have been many different solutions, including least squares, polynomial approximation, smoothing spline, and Takhovnov regularization. The heuristic for this thesis uses a relatively simple solution of a weighted sum between neighbors around a point to perform its numerical differentiation. So as discussed, poorly scheduled maintenance can overwhelm an ALC and lead to unnecessary downtimes for an aircraft. Thus, we'd like to design an algorithm to modify PDM schedules with the goal of reducing the maximum work in progress of the system. The algorithm would change induction dates of aircraft in order to reduce the strain of the system. In addition to maximum WIP, secondary metrics of average and standard deviation of WIP, maximum average and standard deviation of queue length, and average flow days will be used. Because in real-world applications, aircraft have a window of days they can be inducted, it's desirable to modify the dates as minimally as possible. We will not enforce this as a hard constraint, but it will serve as the justification for modifying an existing schedule rather than synthesizing an entirely new one. Because the algorithm will output a new schedule, the algorithm can be applied repeatedly, with the old output becoming the new input. Now I'll discuss the algorithm in greater detail in this section. So before discussing specifics of the heuristic, it's worthwhile to give some intuition and provide an overview. Before algorithmically modifying an induction schedule was attempted, manual modification was tried. It was found that moving aircraft from areas of high WIP to areas of low WIP was generally a good strategy. If an algorithm were to do this, it would need to identify the most susceptible high and low points to shift aircraft around. Derivative tests, as we discussed, can identify local extrema, and these can be used as the susceptible high and low points. The heuristic will be trying to identify the maxima to break them up and identify the minima to fill them in. I'll be referring to these maxima as peaks and the minima as valleys. That intuition is nearly the entire algorithm, but I've also provided an overview. We'll start by finding the first and second derivatives using a numerical differentiation technique, and then apply a second derivative test to those derivatives. This will give us a list of local extrema that we can shift aircraft around. We'll try to pull the peaks apart and push the valleys together to reduce the global WIP. So the first step of the heuristic is obtaining the numerical derivatives. We'll use a simple and easy to implement technique. The numerical derivative will essentially be a glorified weighted sum. We'll sum the values to the left of the point of interest with a positive weight, or I'm sorry, to the right with a positive weight, and those to the left with a negative. Values close to the point will be given a large weight, and those further will be given a smaller weight. The function f here has those desired properties. Here, I represents an offset of days from the point of interest. The parameter n is the weighting parameter. High values of n yield weighting schemes that decay quickly. That is, values close to 0 will be weighted significantly higher than values far away. Low values of n decay more slowly. Values are weighted more evenly. Through experimentation, it's found that a value of n equals 0.02 works well for this application. With this weighting function, the numerical derivative is given by this expression at the bottom of the slide. The parameter w is the window size, which controls how far away the numerical derivative looks. Through experimentation, it's been found that a value of 250 works well for this application. This differentiation operator can be applied successively to obtain higher order derivatives. We'll use that to compute the second derivative. Once the numerical derivatives are calculated, we can use that to detect extrema. We'll use an application of the second derivative test to do this. Extrema will be further filtered by checking if there are a certain number of standard deviations away from the mean. Exactly how far will be controlled by the parameter e. For the extrema detection algorithm, we'll start by taking the first and second numerical derivatives as described on the previous slide. We'll also take the average and standard deviation of the WIP. However, these statistics will be taken over a restricted domain to throw out data when the simulation is ramping up at the start or ramping down at the end. Finally, we'll identify an extrema if it satisfies these conditions. The first derivative, changing sign algorithm, we'll start by taking the first and second numerical derivatives as described on the previous slide. We'll also take the average and standard deviation of the WIP. However, these statistics will be taken over a restricted domain to throw out when the simulation is ramping up or ramping down. And finally, we'll identify an extrema if it satisfies these conditions. So the first derivative changing signs indicates an extrema by derivative tests. and the second condition filters for small extrema. After an extrema is identified, we use the second derivative to sort it into peak or valley. Once the peaks and valleys are identified, we'll modify the induction schedule around those points to try to break them up. The specifics on how we modify the induction schedule are controlled by a set of 6 parameters, 3 for peaks and 3 for valleys. The parameters control the number of aircraft that get shifted around an extrema and the number of days that they get shifted by. The window parameters set the number of aircraft that get shifted, and the left and right shift parameters control the number of days that aircraft get shifted. Specifically, they set the number of days that the aircraft furthest to the left and the aircraft furthest to the right within the window are shifted. Aircraft between those two ends are shifted by a number of days calculated from a linear interpolation. These sets of parameters will be referred to as the peak parameters and the valley parameters. And the results, you'll see 3 numbers separated by forward slashes, and those numbers will refer back to these parameters. These parameters have a large impact on the quality of the algorithm. Generally, they'll be set so that around a peak, aircraft to the left of the extrema get shifted further to the left, and aircraft to the right get shifted further to the right. Around a valley, aircraft will be shifted to the aircraft to the left will be shifted slightly left, and aircraft to the right will get shifted even further left to pull that valley in. So for the statement of this algorithm, I've dropped the subscript on the parameters W, R, and O, but note that they should correspond to either a peak or valley, depending on the type of extrema. Here, A sub k refers to the induction date of aircraft K. The first step in the algorithm is trying to identify the set of aircraft around the extrema. It does this by finding the first time the average induction date exceeds the date of the extrema. This may be a slight overestimate, but is good enough for this purpose. Next, we'll set new induction dates for aircraft according to a rounded linear function. It repeats these steps for each extrema. The rest of the algorithm cleans up by ensuring that new dates are inside the simulation runtime and that any remaining induction dates are left unchanged. So now I'm going to go through an example of the extrema detection technique. We'll start by finding the first and second derivatives using the numerical differentiation technique. We find where the first derivative changes signs, and this should correspond to our local extrema. Looking back at our original whip function, this seems to be mostly accurate. We identify each of these extrema as either a peak or a valley based on the second derivative. And finally, because the last peak is too close to the mean, we'll throw it out. We end up with 1 peak and 1 valley. Now that we've identified the extrema, we would then go back to the induction schedule that generated this result and shift the induction dates. As the heuristic was being tested, some flaws were identified and corrected. Often the extrema detection algorithm interpreted a trail of zeros at the end of the simulation as a valley. To remedy this, an additional condition was added to the extrema detection. All extrema must pass this condition to be identified by the algorithm. It checks if any value past a potential extrema is non-zero. If it fails this, that indicates that the simulation has effectively ended. I'll show an example of why this change was necessary in the results section. Another issue was the heuristics dependence on parameters. To alleviate this, the algorithm was modified to accommodate more dynamic parameters. That is, rather than the number of aircraft to be shifted and the number of days they get shifted being fixed values, they are instead of multiples of statistics of the results. The number of aircraft to shift becomes a multiple of the work in progress at that extrema, and the number of days that aircraft get shifted is now a multiple of flow days. Under this modification, the parameters become factors rather than fixed values. So now that I've talked about the algorithm, I'll discuss the results of testing. I'll talk about the experimental design, then go over the overall results and talk about a few specific aspects that I want to highlight. So to test the developed heuristic, 16 input schedules are created. 4 of the schedules were created from Air Force data and used during the development of RAM. These will be called expert schedules because they were hand-created by an expert. These served as seeds to create 3 more schedules each: constant, uniform, and exponential. In constant schedules, aircraft are inducted at a constant, non-stochastic rate. In uniform schedules, arrival time of aircraft are uniformly distributed. And finally, in exponential schedules, the inter-arrival times are exponentially distributed. Because each of the expert schedules have a unique simulation run length, each of the 16 schedules can be uniquely identified by a combination of their distribution and their simulation run length. Thus, I'll be referring to them using that combination. For example, Uniform 2000 denotes a particular schedule. So during preliminary tests, it was decided that the 6 parameters relating to shifting induction days were most important. 4 sets of peak parameters and 4 sets of valley parameters were chosen so that a 4x4 Latin square design could be created. The design was created with respect to the distribution used in the seed schedule. This allowed us to calculate statistics such as the effects of parameters while minimizing the effects of other factors. Because the heuristic can be repeated multiple times, each test was performed with 5 repetitions or iterations. And after the 16 runs were performed, the heuristic was further tested using the same schedules and hand-picked parameters. And here are the raw results. So the start max whip column tells you the maximum whip before the algorithm was applied. Next to that, the minimax column tells you the best maximum whip the algorithm was able to achieve. The difference between these columns is shown in the improvement column, and the percent improvement is given in the last column. A total of 21 out of the 31 runs saw improvement. Out of the 16 schedules, the algorithm was able to improve 12 of them. And of successful runs, there was an average of 8.7% improvement. For maximum whip, yes. So here's some examples that the algorithm was able to improve. The first example was a uniformly distributed schedule, and within 2 iterations, the algorithm was able to reduce the maximum whip by 9. This was a 23.1% reduction. Other secondary metrics, such as the average and standard deviation of both the whip and the queue, also went down. We see that the large peaks and valleys get dissipated. Second example shows a similar reduction in an exponential schedule. The maximum whip reduced 12.5% from 16 to 14. And again, the secondary metrics were also successfully reduced. On the other hand, some of the schedules tested were difficult to improve. This was caused by little variance in the whip with few large extrema. The constant schedules in particular performed poorly due to this, with only a single schedule from a constant distribution being improved. Figure 8 here shows all the schedules that the algorithm was unable to improve with any set of parameters. However, the algorithm was able to improve all other schedules. So as discussed in the methodology, the algorithm was modified to remove extrema detection at the end of a simulation. Figure 9 is an example schedule that demonstrated the importance of this change. Before this modification, the heuristic identified a valley at the end of the simulation. As a result, the large pile of whip formed just before the end of simulation. The same schedule was run with the same parameters after the modification. We see that this prevented the whip buildup at the end of the simulation. This change allowed the algorithm to more consistently reduce the whip without creating new maxima. So the heuristic was run with 5 iterations for each test. Some schedules tended to improve across each iteration, but most improved within a couple and then became worse. The best iteration to stop at averaged at 2.4. In general, as you might expect, smaller shifts tended to require more iterations. It was very rare that after the heuristic produced a better result, or after it produced a worse result, it then would go back and produce a better result. Almost every time, it continued to improve until it couldn't anymore. Thus, for applications of this heuristic, it's recommended that the algorithm be repeated until a schedule that is worse than the previous one is produced. Then the best one can be taken. So now I'll conclude and talk about areas for future research. So while the heuristic discussed in this paper has shown success, there's still more work that can be done to improve it. I have 3 suggestions for future research. First, I discussed that we wanted to change induction dates as minimally as possible. However, this was not a hard constraint on the algorithm. Future research could be done to add these constraints in. I could limit the number of aircraft, the number of days an aircraft could be shifted to produce more realistic schedules. Secondly, after some modifications, the algorithm was able to dynamically change the number of aircraft to shift and the number of days that it gets shifted by. Currently, though, the number of shift days is based on an overall statistic of the simulation and does not take into account any specifics surrounding the extrema. For example, rather than looking at the average flow days, it could instead look at the flow days of a particular aircraft it's shifting. Finally, future researchers could utilize the WIP data around an extrema. Currently, only the WIP at the extrema is being used in the heuristic, and crucial information about the WIP around it is being ignored. For example, if the algorithm sees that there's a valley adjacent to a peak, it could shift the aircraft from the peak into the direction of the valley. Currently, the aircraft in the peak area is being dispersed without regard to its surroundings. So in conclusion, I developed a heuristic algorithm to alter depot maintenance induction schedules in order to reduce the maximum work in progress. The algorithm utilizes the ramp simulation tool to obtain results on induction schedules. The algorithm keeps most of the induction schedules unaltered by manipulating aircraft only around large extrema. The algorithm detects important extrema and is able to push together aircraft around valleys and pull apart aircraft around peaks. The algorithm was successful in reducing the maximum WIP for 12 out of the 16 schedules tested. The algorithm works well for certain input with well-tuned parameters. However, for an already well-optimized schedule or with poorly selected parameters, the algorithm can perform poorly. Modifications to the algorithm have improved its performance. However, there's still additional work that can be done to further increase this performance. And that concludes my presentation. I'd like to thank the faculty on my committee, especially Dr. Schultz and Dr. Biswas, who have been giving me great feedback all year. And I'd like to thank everyone at Merck who contributed to RAMP and made this project possible. I'd be happy to take any questions now.
Of those, of course, we've talked about this a lot. We've lived and breathed this project for 2 semesters now, and great presentation.
Thank you.
Of course, I know all this stuff, so that's coming from someone who's lived it with you. And so I'd be interested to hear some of the other questions. The one question I do have is on the hard to improve schedules. Okay. Why are they hard to improve? What is your intuition tell you on why they're hard to improve?
So I think it has a lot to do with not having pronounced extrema. For some of these schedules, there are some small extrema. Like on this run 4 here, there's a little bit of a peak here, but for much of the simulation, it looks more like noise than actual extrema caused by the underlying patterns of the function. So I think that an algorithm relying on abusing those extrema is going to perform poorly when those don't exist.
I believe because you chose your average to be kind of the base to select the extrema and the value, right?
So repeat that again.
Your average of WRB kind of the base selecting the extrema as well as the value.
Yeah.
So when there is not much difference from the base, it is really hard to pick up the value as well as the extrema.
Right, like in this example with this peak being thrown out because it's too close to the mean.
Inside the bars.
Right.
Yeah.
we can basically go forward and instead of using the mean.
Well, I mean, in some cases, it's just a good schedule.
Yeah.
It's just a good schedule, and you're not going to make it any better. It's better in the sense of we're trying to have as many aircraft available in service, so reduce that maximum.
So even remember, we had some kind of problem in the regular, the good one too, where we have the value and peak. But sometimes when the peak is too close to the mean, remember when like that peak right there, I think you cannot identify that peak, that round one, right? Or the right there, which is close to the mean. But we can see there is a peak a little bit. We are not talking about that one which has almost the similar, noise or nice curve. But still, whenever it is close to the mean, it is not detecting the peak or the valley.
Right.
But it's the it's the 7 aircraft in this example that we want to get down to 6 or to 5. So maybe it's okay not to mess with that peak.
I understand. We saw the problem where we have a lot, but still it's not catching up because of the.
And maybe a solution to that could be like shrinking those bars until it finds a valley or a peak.
That's true too. You could squeeze those dotted lines.
Right. So on a first iteration, it would address this peak, and then if that starts to get too close to the mean, and now this guy's the highest.
I'll say one thing is, as you're giving your presentation, one thing that I was just thinking about was this all began because we looked at a graph as a human looks at a graph and says, hey, what if I move some, change some of my induction dates in order to get rid of these, these high points. And that's all I gave you. I said, this is what we did. Now, can you turn that into algorithm? And you have successfully done so. And, that's very different from any kind of work I've done in the past. Is, because basically you're taking a human look at something and you're turning that into how can I automate what a human does? So I've enjoyed this project from that perspective. I don't know. Have you ever run into when developing algorithms in the past, a lot of it's based on intuition and everything.
It is kind of like that. It is always, especially the combinatorial optimization, is always kind of based on
intuition, right?
Yes.
Whereas this one said, okay, what does a human do visually? That's very complex.
Right.
It seems simple, right? Oh, find the peak and but you've been able to take what a human does visually and turn it into an algorithm. And that's impressive.
So let's hear from our audience.
Yes.
We already know what's going on.
Yeah, that's the thing. We're so in tune.
Whether they know it or not.
Right.
So, Harrison, thank you very much for the presentation. It was great.
Thank you.
I would like to go to the slide with the overall results of each of the, I believe, 30-some runs, if you don't mind.
Absolutely. Yeah, I know there's a lot of information on this slide.
Yes, but one that I wanted to particularly focus on was the schedules that were developed by the experts. Now, within that context, how well did your simulation model work compared to just not the constant exponential, like the uniform, take all those out? Because the expert schedules are, that's a kind of like the high bar that you need to compare against. So did you actually do a separate a run compared to just the experts?
So no, I did not isolate the expert runs from the rest and do a separate analysis. Within the initial 16 runs, I was able to improve 3 out of the 4 expert schedules. So you can see, it's hard to navigate the mouse because it's on the other screen. But over here, we're getting,
So now what you do the duplicate.
Oh,
thing.
yeah.
You do not need any presentation. So go to the duplicate mode and.
Can I leave that open?
No, not there.
What?
Not there. Go to the open the PowerPoint. Just
Well,
go to the PowerPoint view. No, go to the PowerPoint view.
This should work now.
Yeah. Okay.
Yeah.
Sure.
Okay.
Technology.
Yep. Oh.
You have to share your screen. We're no longer seeing your screen. But that's basically what I saw too, Harrison. Looking at your comparison, when you look at everything, you're saying that it improved 12 out of the 16. But if you look at just the expert, it would seem that you are still improving against an expertly developed schedule, which even further validates your work more than by presenting it in this aggregate form. So I just wanted to make sure that you understood and people observing this presentation understand that this actually is working better than how you even present it, in my opinion, because the just the expert component where I saw improvements, you would expect not to see improvements on a schedule that experts have made. But if you're actually making improvements upon an expertly scheduled schedule, then that's great. That's amazing, right? And was there a situation where your model did worse than the expert, or was it at least as good or better?
So like on run 6 there on expert 3000, I'm reporting a 0 improvement, and that's because I'm taking the best run, even with including the initial schedule. So all of those 0 improvements are basically showing that I did not improve.
Yes, but the question is, did your model, the best model that you produced from your model, was it ever worse than the expert? Or was it at least as good?
That's what I'm trying to say. The ones that have 0 produced worse results.
Oh, I see. Okay.
It does not start, the algorithm doesn't build a schedule from scratch.
Right.
It'll take an existing schedule and try to modify and try to improve it, just modify it. So we're not taking an induction, we're not taking a blank sheet and building an induction schedule. We take an existing induction schedule and tweak it a little bit and see if we get better results. Okay. And so you can't get worse because you're taking the best of all the iterations.
Right.
So it's some, you could start trending in a bad direction, but you're throwing those out. Does that make sense, Dr. Choi?
Absolutely. Thank you. I guess I was trying to observe the mechanism. So I guess, is there a way to infer a little bit deeper into the data, in a sense that I understand that this why it's 0 and not a negative, but whenever it did the improvements, did it?
You're showing the worst case here, right?
Yes. So
your
this
worst
is.
result. You also should show your best one.
Yeah. Yeah. This is the example, and I showed the initial schedule, this iteration 0, within the presentation, but I said that I wasn't able to improve it, but I didn't show what the algorithm did to it.
It didn't do too good in this one.
No.
But this was 1 out of 30. Most of the times it did well. And when we're visualizing it, people in the audience, iteration 0 up there in the top left, that's a very smooth curve. And then we start seeing all these peaks and valleys. I like to say peaks and valleys rather than extrema. It's we're trying to get rid of those, and in this case, we're creating them. So this is an example that did not do well. But Harrison, maybe you take the same thing.
Yep. Show a
Because
good
what
one.
we're doing is iteration 0 starts with an
Good one.
induction schedule, modifies it slightly, then you get to iteration 1, and then you start modifying iteration 1. So that's why he says the output from one run is the input to the next run. If that makes sense.
Thank
Okay,
you
now
for
here's a good
clarifying that. Like, that makes a lot more sense. Thank you.
See,
I
here's
understand
where they
now.
got better and better and better.
Right. So this was the initial schedule. And the first iteration was able to knock off this peak here. And then by the second iteration, it improved it more. And I think by the third, fourth, and fifth, it's starting to kind of stagnate some and not improve and start to produce like fluctuations. So if I was looking at this, I would probably select schedule 2 or 3.
And here's why I asked that other question of why I think you were able to improve this one rather than number 6. Look at your red line. The red line is an actual queue. The blue line is the actual number of aircraft that are in the system. The red line is those aircraft that no work is being done on. You've got area under the red curve in this one. You have no area under the red curve in run 6. So there's not
much to improve on.
There's no opportunity to improve it.
Yeah.
I mean, all you can do is make it worse. So that's why I think you did better on this run 15.
I'd agree.
And this was this an expert schedule or just a?
This was, I think, exponential uniform.
Okay.
This was uniform.
Uniform. Okay.
Yeah. So you can see the statistics improving here.
Why don't we show one expert one that has been improved?
Yes, you can be an expert.
Yeah. So a good one to select would be 7 or 8. I think 7 is that one that was was this guy. This was 7. So this is one of the expert schedules.
That's a schedule that's out of control.
Right. And we were able to improve it.
That's Robin's Air Force Base.
But but I think this one is better. So this one reduced in the first iteration, it reduced by 3. So you can see a lot of the little peaks were just taken down a little bit. There's not a lot of area.
Not a lot there. Oh, well, but the scale is very different.
Sure.
I mean, you say there's not a lot, but you got 8 or 9 aircraft sitting in a queue.
True. Yeah. It looks like we get up to 10 there.
Yeah. So that's 10 idle aircraft that you have an opportunity to, keep back in service.
Yeah. And we do see that improving there.
And the other thing is all we're doing is modifying an induction schedule. We're not adding resources or, to the process.
Right.
You're not adding additional docks or additional manpower. All you're doing is changing when an aircraft comes in. So it's a very inexpensive change in order to get more aircraft active duty. There's no cost to anybody.
Right.
That to me is one of the most impressive points of this. There's no cost. There's no cost to the Air Force.
So yeah, you might be able to see this was done before the end valley.
Right.
Any other questions?
So actually, I had one. Harrison, this is Daniel Edwards.
Yes.
You talked about incorporating other constraints into the model. Based on what you've learned so far and knowing that the Air Force requirements for induction schedules and maintenance intervals are so tied to date ranges, flight hours, how would you go about approaching incorporating constraints like that into this model?
That's a great question. I think to start off with, I would naively just like say, okay, dates can't be shifted by this much. If over a certain number of iterations it goes outside that range, it'll push it back inside. So I would probably start with seeing how that works, and then making improvements from there.
Okay. And I did just want to point out, this is an example of digital engineering is the buzzword in the Air Force. And they just had a briefing in the last 2 weeks where they talked about eliminating the inefficiencies in the ways that they do business, where things are done in an expert manner by people who are sitting down and crunching the numbers by hand. So this ties right into very, very relevant topics, and just great job.
Thank you. Okay, anyone else?
Okay, well, it sounds like there's no other questions. So
Yeah.
Harrison, thank you very much. Dr. Choi, if you could stick around, we'd appreciate it. And we want to thank everyone who joined us in the audience, even though we can't see you. Maybe we can. Maybe Harrison will get us. There we go.
No.
Yeah.
Oh, yeah.
Yeah. All right.
Okay.
Thank you all very much.